pavilion.
I might put on a Pikachu hat and that's as far as I'm going.
Like someone stop there.
Why stop there? Lie makes yourself yellow.
Hey, whoops, not that much to get paid. Pay yourself.
So we are going
I'm
to
too sweaty to rent to myself, just call myself a sandwich.
Yule-Walker equations for an AR2 model. The Yule-Walker equations are useful in determining the coefficients of an AR2 model if the autocorrelation function is given. If you recall correctly, for an AR1 model, what was the autocorrelation function?
Wasn't it when h is greater than or equal to 1?
Keep going.
V1 to the power of h,
Absolutely.
absolute value. And 0.
Zero otherwise.
Zero,
Right. So what does this mean? We actually picked out the value of V1 from the PACF, if you recall correctly. I just, picked V1 out because when h is equal to 1, it would equal to the correlation rho 1. So great, it's easy when it comes to an AR1 model. But when it comes to an AR2 model, we have V1, we have V2. So we need some extra work here. Let's say we have an AR2 model. And an AR2 model can be expressed as yt equals V1 yt minus 1, V2 yt minus 2 plus epsilon t. Correct. Now, Yule-Walker equations are amazing because we can transform them into matrix form. First step. Call that equation 1, and I'm going to multiply 1 by yt on both sides. And we are going to assume a mean zero series. By all means, I don't have to assume the mean is 0 in this case.
Should that be yt minus 2? There's data 2.
Oh, thank you. So I'm going to take expectation on both sides. Yt times yt is yt squared. I can pull phi1 out because it is a constant. Same with phi2. Nothing to pull out in the last expression, so I'm going to leave that as is. If we look at the formula for covariance of yt, yt, or yt plus h, whatever, I think I can generalize it by putting t plus h. So that is yt plus h, correct? Minus the expectation of yt, expectation of yt plus h. That's the formula. Covariance of x comma y is expectation of xy minus the expectation of y multiplied by the expectation of x. So the expectation here and there are 0 because the mean of the series is 0. So pretty much in this case, covariance of yt, yt plus h is equal to the expectation of yt multiplied by yt plus h.
Wait, so those ones are 0 because the mean is 0, is that what you're saying?
Yes. So which would give us P1? Yt and yt minus 1. That will go back to the variance of yt itself. Confused if you're looking in the textbook. There is a mu. Yt minus 1 since gamma h is covariance yt plus h. Yes. And if that is the case, what is expectation of yt times yt minus 1? So I went from here to there, so that is gamma h. My question to you is, if that is gamma h, what is expectation of yt times yt minus 1?
Either covariance of yt comma yt minus 1.
Correct. So in terms of gamma, how can I write that?
Get the negative 1.
Gamma negative 1. What about that term?
Gamma negative 2.
Gamma negative 2. The last one, it would come down to the variance. Why? If you look at expectation of yt comma epsilon c, we can't directly say that it is going to be 0 because I have phi1 yt minus 1, phi2 yt minus 2 plus epsilon t multiplied by epsilon t. Correct. All I did was take yt and plug it in there. So the noise, what is the noise I have that got added to the series it is not going to be correlated to the series value from yesterday. It is not going to be correlated to 2 points, in the past, but it will be correlated with itself. So the last part would reduce to expectation of epsilon t squared. Here I'm going to write gamma minus 1 as gamma 1 because
It's the same thing.
same thing. Phi 2 as gamma 2. Last term, epsilon t squared. Expectation of epsilon t squared is simply the covariance of epsilon t, comma epsilon t.
Wait, how do you get the epsilon t squared?
Epsilon t times epsilon t.
And the other values just don't matter.
They are 0. Because the random variable at time t minus 1 will not be correlated on some random noise.
Okay.
Same with t minus 2. So here, expectation of epsilon t squared would become covariance of epsilon t over epsilon t, which is the variance of epsilon t. So we end up getting sigma squared. Because of our standard assumption that epsilon t is normal with mean 0 and variance sigma squared. So gamma naught is equal to phi 1 gamma 1 plus phi 2 gamma 2 plus sigma squared. If I divide by gamma naught on both sides, that's what I would have, right? What is gamma 1 over gamma? You can go back and look at your notes.
Or gamma H.
If you divide by gamma naught, it is going to become rho 1. You can't say O.
Oh, I just said O. So I was right, H. Or is it row? I can't tell with your handwriting.
Good. So that's what we would have. Our objective now is to find row 1 and row 2 so that we can find gamma naught. So say this equation. We multiply both sides by yt to get gamma naught. What should you multiply by both sides to get gamma 1? Do you follow my question?
No,
We multiplied both sides, the equation, the AR2 equation, by yt on both sides to get gamma naught. What should we multiply on both sides by in order to get gamma 1?
YT plus 1.
Okay, yt plus 1. I'm going to do yt minus 1 because why not? It'll be easier to see.
This is for the gamma 1.
Yes. So that is our original equation. Phi1, yt minus 1, Phi2, yt minus 2, plus epsilon c. Multiply both sides by yt minus 1. So yt minus 1, yt equals Phi1. Yt minus 1 times yt minus 1. Phi2, yt minus 1 times yt minus 2. Yt minus 1 times epsilon t. Good. So, right here, when I take expectation, what would happen? Take expectation on both sides.
First.
So we will have expectation of yt minus 1 yt equals expectation of Phi1 yt minus 1 yt minus 1 plus expectation of Phi2 yt minus 1. I am going to rewrite yt minus 2 as yt minus 1 minus 1. I did nothing wrong, correct?
Well, then you have to do your YT with the epsilon. Your next, yeah.
What do you mean?
I said you just missed your other class term. You finished it.
So expectation of yt minus 1 times yt. You can pull Phi1 out. Expectation of yt minus 1 yt minus 1. You can pull Phi2 out. Expectation of yt minus 1 yt minus 1 minus 1.
Ahead of us.
Plus expectation of yt minus 1 times epsilon c. So we know the time point from the past is not going to depend on the noise at present, right? There is not going to be any relationship, so the covariance there would be 0. That is a covariance. So in terms of gamma, what is that? Is it gamma 0, gamma 1, gamma 1? Good. The time indices are the same, right? So if I call S to be equal to t minus 1, this would just be y sub s multiplied by y sub s. So what would the expectation of y sub t minus 1 squared be? look at the formula. That's a bit correct. Okay, that is the race. I should have kept it here. One. To make things easier, let's just say yt minus 1 is s. A different type of index, right? So you are pretty much doing expectation of ys squared. Last time, expectation of yt squared reduced to what? Gamma naught. So this would become gamma. What would that end up being? So I have expectation of ys multiplied by ys minus 1. Ys multiplied by ys minus 1 in terms of gamma. Gamma negative 1. But gamma negative 1 is the same as positive.
And the last term is 0 because there's just no correlation at all.
Yes. Correct. I'll put it as gamma 1. Good. If I divide by gamma not on both sides, I will have gamma 1 over gamma naught equals P1 gamma naught over gamma naught plus P2 gamma 1 over gamma naught. What would that equal to? Rho 1. Phi1, that's just 1 plus Phi2 of rho 1. Correct. So we can rewrite this if we move the rho 1 to the other side, rho 1 terms to the other side. We can come up with the autocorrelation for the series. So rho 1 minus P2 equals P1. So rho 1 would be equal to P1 divided by 1 minus P2. That is the formula for rho 1 if we know what P1 and P2 are. Good. But in practice, our goal is to use a series to find P1 and P2. So the equation of importance is rather that. Correct. So we're going to use this if we know P1 and P2. But if we don't know P1 and P2, we've got to make use of the sample autocorrelations to estimate the value of P1 and P2. Do we agree? Okay.
So just double check the one we did before was for gamma, and this one's for gamma.
What?
Just still check. The last thing we did was for gamma naught, this is for gamma 1.
Yes.
And can you repeat that last bit you said?
So I rewrote to find rho 1, right? If we know Phi1 and Phi2 in the series, then we can compute a value for rho 1. But in practice, we have a realization of a series. Our goal is to find P1 and P2. So in order to find that, we will make use of the sample autocorrelation to solve for phi1 and phi2. Does that make sense? Okay. Yule-Walker equations are quite important, and you will see why. Now, this is what I want you to do. We multiply both sides by yt. We multiply both sides by yt minus 1. Sure, I can multiply both sides by yt minus 2, but I'm trying to get a general expression. So I want you to multiply both sides by yt minus j. And tell me what you get right over here.
By the way, you said it's a sample of autocorrelation or whatever. Is that the thing you had boxed up or?
This?
Yeah.
Row 1 is the sample autocorrelation. Row 1. But row 1 right now, this particular formula says that I could use an estimate for row 1 using the autocorrelation that we can come up with for a series to find phi1 and phi2.
Okay.
Very accomplished.
What we're going to do is we're going to multiply both sides by yt minus j, right? So I'm just going to use my space here instead of erasing everything. You can understand it better also. So yt minus j, yt minus j, yt minus j, yt minus j. Good. So yt minus j, yt minus j, yt minus j. And that would be yt minus j. Good so far. So the key here is to match the time indices, right? If I can match them somehow, then I can come up with the autocovariance. So how do we do it? So this is the trick that I'm going to employ. We know that's going to go to 0, so I'm going to drop that sentence out. So I'm going to rewrite yt minus j, yt minus 1 as yt minus j plus 1 minus 1. Okay. Multiplied by y, t minus 1. Good. Plus expectation, phi2, y, yt minus j plus 2 minus 2 yt minus 2. The time indices are j time steps apart, so this would become gamma j, right?
Okay.
So over here, have y t minus 1, going to write t minus 1. I have minus j plus 1. I can write it as minus, if I pull the minus out, j minus 1. Correct? Yes. This term, I'm rewriting it that way. T minus 1, pull the minus out from negative j plus 1 to get that. So that would reduce to expectation y t minus 1 minus j minus 1 y t minus 1. Good. Did I get the time indices to sort of match here so I can make a substitution? Last time I used s plus phi2. Same trick. Y t minus j plus 2 minus 2. I could write it as t minus 2. If I pull a negative out, I have j minus 2. Correct? So that would become expectation of y t minus 2 minus j minus 2 y t minus 2. Good. So these two match, correct? And they are j minus 1 units apart. So we're simply finding, say if I call that t minus 1 as s, I'm trying to find y s minus j minus 1, comma y s. Correct? What would that reduce? Gamma j minus 1. So rho j, excuse me, gamma j is v1 gamma j minus 1 plus next term.
Wait, so it's gamma j minus 1 because the y-s's kind of disappear?
Yes. If I call t minus 2 as, say, p, I will have y p minus j minus 2, comma y p. That expectation is merely the covariance. So yp time indices match. How many units apart are they?
J minus 2.
J minus 2.
So even though it says minus j minus 2, it doesn't really matter, it's just j minus 2 apart.
Because of symmetry,
Okay.
right? In this case, it would be gamma minus j minus 2, which is the same as saying gamma j minus 2. So that term would become p2 gamma j minus 2.
Just make sure it doesn't become like j plus 2 or something.
Or you could do it with the next one.
I get it.
If it was pluses.
Good. If I divide by gamma naught on both sides, gamma j over gamma naught is rho j. Rho j minus 1 times v1, v2 times rho j minus 2. And that will work for j greater than or equal to 1. Good. If you plug in 1, rho 1 would equal to phi1 rho naught plus phi2 rho negative 1. Go back and look at the rho 1 that we derived. Does it match up? Yes. So this would simply be the Yule-Walker equations or general form of Yule-Walker for an AR2 model. So if I plug in J equals 1, I'll get one equation. If I plug in J equals 2, I'll get another equation. So
Because rho naught is equal to 1, right?
what?
When you plug in J equals 1, you end up with phi1 plus phi2. I just forgot the name of that p thing.
Rho.
Rho.
Not P, it's not a P.
2 minus 1, row 1. P2, 2 minus 2, row 0. Correct. I'm just plugging in J. This would mean row 1 is P1. Row naught is simply 1 plus P2, row 1. Row 2 is P1, row 1 plus P2. Correct. Would we call that a system of linear equations? Could we? If you know row 1 and row 2, that's a number, that's a number, that's a number, that's a number. It would become a system of linear equations. So if you know the sum of odds and correlations, we can find phi1 and phi2, and if we can find phi1 and phi2, we can easily find the coefficients, right? Which is why, when we first started, I mentioned AR model is easier to fit than an MA model. So we will use the matrix form to find P1 and P2. We'll do an example on an AR2 model using this next time.